So a distributed last level cache is logically a single cache in that a data block will not be replicated like it would be in private caches, where if 2 or 3 or 4 cores, for example, read a block, each of their caches would have that block. And thus, really, the total capacity of the caches is not how much memory we are covering, because some memory appears many times, possibly, in these caches. A last level cache that is distributed is logically still one cache, meaning if its capacity is, let's say, 4 megabytes, then we really cover 4 megabytes of memory without any replication. But this distributed cache is sliced up so that each tile, which contains a core and possibly local caches, now also contains a part of this cache. So now what we have is, in our mesh, we have a tile that contains a core, a level 1 cache, a level 2 cache, and a slice of the L3 cache. So if this slice here that we use per core is, let's say, 1 megabyte, is really n times 1 megabytes, where n is the number of cores. So now, as you can see, if we use 4 cores, we get 4 megabytes. With 16 cores, we have 16 megabytes, so we get what we want. The big cache that is there to prevent memory accesses is growing with the number of cores, but it doesn't have a single entry point. In fact, each slice has its own entry point. So if we want the data that is in this slice, we have to route our message to that slice. If we want the data that resides in another slice, we send a message there. If the data is spread among the slices so that all of them get equal demands for the data, then the network traffic would be nicely distributed across our chip so that none of the links get overutilized. But if we have a level 2 miss in a particular core, how do we know which slice of the level 3 cache to ask for the data? One simple solution is to spread the cache round robin among slices by cache index. So if we have our level 3 cache with, let's say, 1024 sets, slice 0 gets set 0, slice 1 gets set 1, etc. And then let's say that we have 8 cores. Then slice 7 gets set 7. Slice 0 gets set 8, set 9 is in slice 1 again, and so on. So now we can relatively easily, after we break down the address to access the cache, we know the set number, and the least significant 3 bits in this case tell us which slice to ask. If we have even more cores, then the number of sets in the cache will grow, and as a result, the number of bits that we need to tell us which slice we have is growing, and that means that the number of bits in the index are growing, and we will need additional bits to tell us in which set to look. Note that if we sequentially access data, then we will be really looking at one set, and then the next set, and then the next set, and this nicely spreads the load among the slices of the level 3 cache, because sequential accesses are basically going to be spread across the entire chip. However, the spreading of blocks round robin across the entire chip may not be good for locality, because a core is just as likely to access something that is in the opposite corner of the chip as it is to access its own slice, in which case there is no on-chip network traffic whatsoever. So another way that can help with that is that we spread the data around, but this time we spread it by page number. So all of the blocks that belong to the same page would end up in the same slice of the level 3. That helps because now the operating system can map pages so that it makes the accesses to L3 more local. For example, here, this core is running a thread that has a stack. The pages that belong to that stack should be those that end up in this slice, so that if you have a level 2 miss, we are very likely to access our own local slice of the L3 cache. Of course, some of the shared data will be elsewhere, but this dramatically improves the locality in terms of how far do we need to go to get to the correct slice of L3. Any data that tends to be accessed by one core can be now mapped by the operating system so that it's usually found in the local slice of the last level cache.